one of our goals is to be able to find a way to generate every pattern. See, we have some wonderful tools that we can test a certain pattern, and we can certainly test lots and lots of different possible patterns, but we want to get a way that will consistently get them all. After all, we want to get them all. That's one of our goals. And in the process, we'll find ways to describe these patterns, and also we're setting ourselves up to be able to count how many different patterns are there with certain characteristics. We have a few special cases, but we really just want to nail down a very general. We want to say, look, it has period n, has b-balls, how many are there? Now, we're not going to get the answer today, but we're going to set ourselves up for that answer soon. Where we're going to start is by asking a very simple question, really an observation, if you will, saying, what are some things we can do to change our juggling pattern and produce a new juggling pattern? So let's start with the following observation. If we have a juggling pattern, so we think of it as a series of throws, throw 1, throw 2, up to throw n, so there's our list of our throws, then we can change by taking any one of our throws and either going up by some multiple of n or going down by some multiple of n. If we go down, the only thing is we can't go negative. The claim is that's still a juggling pattern. Now, why? Well, what's happening here is, if you think about it, we have our test for a juggling pattern says, look, do your modulo n. In other words, see what happens when you divide out by n. So if I increase by some multiple of n, when we carry out that modular arithmetic, that multiple whoosh, goes away. So if I was a juggling pattern before, I'm a juggling pattern after. So that's good. So that's why we can go up and down by multiples of n. Now, one thing we can also say, a little bit more precise, is look, suppose we take one throw, we go up by exactly n. Well, the new pattern will have one more ball. One more ball. Now, we know that because we know that the number of balls is the average. So when we add n, well, to one throw, the net result when we take the average is adding 1, because remember we add up all the throws and divide by n, so we add 1. So that's why the number of balls goes up by 1. Same idea, if we decrease one single throw by a factor of n, then we're going to have a new pattern with one less ball. So this gives us a way to sort of say, well, what if I want to take my pattern with 2 balls and find a pattern with 3 balls? Okay, great. Just add the period to any one of your throws. Now, we can, in some cases, go down if some throw is at least n. Now, if none of our throws are at least n, well, we can't go down any further. Now, speaking of not going down, we have what we call minimal juggling patterns. So a minimal juggling pattern of period n is a juggling pattern, okay, it has to be a juggling pattern, but all the throws are in some sense as low as possible. Now, not to say all the throws are 0, that's certainly if all the throws are as low as possible, but no throw is at n or above. Now remember, we said, hey, if we have a throw that's above n, you can always go down by subtracting n off that throw. So in some sense, minimal juggling pattern says, look, you've reached the bottom floor. You can't go down any further. So that's what a minimal juggling pattern is. Now, one nice thing we can say is every juggling pattern is associated with some minimal juggling pattern. In fact, it's associated with exactly one of those minimal juggling patterns. And how do we do it? Well, we say, look, we keep going down. So we look at our period and we say, look, are any of our throws too large? And at that period or above, if they are, we keep subtracting off until we get low enough down. Let's see this with some examples. So here we have some patterns, 6, 7, 9, 2. Let's start with that one. All right, well, that's a pretty nice pattern. It's hard to juggle, but of course, the computers, they can juggle it, so no problem if you really want to see it. Now, what's our period? Well, here we have period 4 because there are 4 throws. So this would have n equals 4. Now, is this minimal? And the answer is, well, no, because we have throws that are above 4. So what do? Well, we start bringing those throws down. They need to go down. So let's just think about it. So 6, okay, too high. Subtract 4, and we can get 2. 7, too high. Subtract 4, and we'll get 3. 9, really high, right? In fact, if you subtract 4, it's still high. So what we can do is we can keep subtracting until we get down to something we're comfortable with. Another way to say it is to say, well, let's just take modular the period and say, what's that smallest positive, or rather, non-negative value? So 9 modulo 4 was 1, right? That's the smallest non-negative number we can take. 2 is good to go. And there we have it. 2, 3, 1, 2. Okay, so there's the answer. 6, 7, 9, 2 is associated with this other pattern, 2, 3, 1, 2. And this is minimal. See, all the throws are below 4. All right, well, here's this other pattern, 5, 2, 5, 1, 2. Now, this is a great pattern. This actually shows up a lot as people talk about juggling, because it's one of those patterns that actually gets a name. Most juggling patterns don't have names attached to them anymore. They just have their side swaps. But this one has a name. It's called the baby juggling pattern. And the idea was, of course, that old vaudevillian performers, well, they would try to incorporate everything into their acts, including their own children. So they would have a child in one arm and some balls in the other arm. They'd throw the balls up very high. And while the balls were in the air, they would switch the child to the other arm so that the balls would come down. And then as the balls came down, they would throw them back up. And then they'd switch the baby again. So what was happening was that the baby was representing a ball. And so the baby juggling pattern gets its name from this idea that there's one ball that never goes high. It always stays low. And you can actually look at the diagram, and you see that's what happens. The 5s, those are high throws. Wow. But the 2, the 1, and the 2, those are low throws. See, 2, you're just holding on to something. And 1 is a quick pass to the other arm. So, now, is this minimal? Well, let's just do a quick check. 5, 2, 5, 1, 2. Well, that'd be n equals 5. You say, well, there's some good numbers here. 2, the 1, 2. Great. But the 5 is too big. Remember, we want all the throws to be less than our period. Okay, so we've got to bring that 5 down. How do we do it? Well, we just say, okay, let's subtract off until we get something that's as small as possible, but still not negative. Now here, it's not too bad. We say, look, 5 becomes 0. 2, good as it is. 5 again, still 0. 1, still good. 2 is 2. And there we go. 0, 2, 0, 1, 2. So that's pretty good. And remember, we said every juggling pattern is associated with some minimal one. It's actually associated with exactly 1. So every every juggling pattern goes to exactly 1 minimal one. Now, why can't it go to 2? Well, the problem is that there's this really consistent rule that says what happens to every single throw. So there's no ambiguity here. And so that's great. So now, in some sense, what we can do is really group things based off of their minimal juggling patterns. In fact, that's the secret of our success when it comes to counting. But of course, well, we'll get to that a little bit later. So recall that we can think of our patterns as being on a circle. That's sort of the advantage of that modular arithmetic. We said we're going from the line into a circle. So let's suppose we're thinking about a pattern with period 5. So we have 5 beats, and we've marked here our beats. 1, 2, 3, 4, 5. And now, when we're thinking about minimal patterns, one of the nice things about a minimal pattern says, look, no throw goes all the way around. See, when we have unlimited throws, sometimes when we have a throw, it could wrap around multiple times before it landed. Minimal pattern says, no, we aren't allowing any wraparound. So anytime we make a throw, it will never go full circle. It'll always stop somewhere a little bit short. So with that in mind, we're going to introduce an important board. So we're going to look at this very particular board. Now, when we think about our balls being thrown, what we see is that they are going to be thrown at some beat and they'll land at some other beat. So we're going to have the rows and the columns of our board correspond to the beats. The rows are going to talk about when do we throw the ball. So for example, this will be at the first beat. This will be the ball we throw at the second beat, the third beat, the fourth beat, the fifth beat. The columns are going to represent when the ball lands. Does it land at beat 1, 2, 3, 4, or 5? Now, so far, we've just said there's a board. You'll notice that there's numbers here. What are these numbers representing? Well, they are very important numbers. And what they are is it says, how far did you throw? What kind of throw did you make? So for instance, let's see if we can look at some of these entries. If I wanted to throw at beat 2, land at beat 4, I'd have to go 1, 2. So the 2, 4 should be a 2. Okay, and it is. What if I throw at 1, land at 4? 1, 2, 3. Okay, 1, 4 should be a 3. Yes! Success! Now, some a little bit strange ones, right? What if I throw at 4 and I land at 3? You want to say, well, I go backwards. No. We always go in one direction. Time moves forward. So if I want to start at 4 and land at 3, I'd have to go 1, 2, 3, 4. So if I have a throw at 4, land at 3, I have 4. So what you're seeing here, these numbers correspond to the throws that achieve your action. Now, where do they actually come from? Well, it's a very simple formula. We know when we want it to land, so that's the column. We know when we threw it, that's the row. So you look at the difference. And then there's a small correction. The correction says, well, if you're down here below the diagonal, so we think of this as the diagonal. So if you're down here in this part, we have to add n. Now, why? Well, normally if you just had the column minus the row, that would be a negative number. If you're down here, we don't want negative throws. So that's why you add n to help boost it up. Now, so far, you're like, okay, great. How does the board help us? Well, here's the fun idea. What we can do is we can now think about what happens with each ball. And what we'll do is we'll say, look, ball 1 is thrown somewhere and it lands somewhere. So maybe ball 1 would land on, when I say ball 1, the ball that's thrown at beat 1 lands at beat 3. So I could put a little marker here to indicate, okay, I threw it at time 1, landed at time 3. Great. All right, how about 2? Well, I can't have it land at beat 3 because there's already something landing there, but I could have it land at, say, beat 4, no problem. Okay, so I'll put a 2, 4. So that ball thrown at beat 2 lands at beat 4. 3, well, maybe it's going to go a long ways, and it'll go all the way around to 2. Nothing's landing at 2 yet. Okay, so I'll put something there. Great. All right, how about at 4? Well, where can it go? Well, nothing's landing at beat 1 yet. All right, so we'll put something there. And 5, well, only one option. Nothing was scheduled to land at beat 5, so we'll put something there. And now we have this nice sort of placement here. But this isn't just any random placement, right? We have a juggling pattern. And notice at every beat, one ball got thrown. At every beat, one ball landed. And we can even just read off the pattern. This is where the numbers come in really, really important. So that's why we like these numbers here. What's the pattern? Well, 2, 2, 4, 2, 0. So there's the pattern. 2, 2, 4, 2, 0. That's it. That's it. So this gives us everything that we want to know. The full behavior of the juggling pattern. We have it right there. So the biggest takeaway from today, and this is the most important thing that we're going to talk about, is that when we think about minimal juggling patterns, we can really think about it as placing these tokens down in a way so that no tokens are in the same row and no tokens are in the same column. So for every minimal juggling pattern, there is a way to put them down, and vice versa. Once I put these down, I have a minimal juggling pattern. Now, we call this something really special. These are called rook placements. And we're going to, in particular, have a rook placement where we have as many rooks as possible. Now, if you're not familiar with rooks, rooks are a piece in chess, and rooks have a special ability to move. They can move any distance in either a horizontal or a vertical direction. So when we talk about a rook placement, it means that we want to have the rooks put down, but we can't have, for example, two rooks in the same row because they would be able to fight each other. I guess rooks don't get along. So in rook placement, the idea is no rooks can attack any other rooks. So that's an example of rook placement. And of course, now it's super easy to make new ones. We just start filling them in. And lo and behold, we can make all sorts of interesting patterns. And now we have another one. So here's another minimal juggling pattern. 3, 1, 2, 2, 2. Okay, well, are there more? Absolutely. We could go, for example, down this sort of opposite of the diagonal, right? And we can say, well, what is this? 4, 2, 0, 3, 1. Another pattern. And pattern after pattern. We can get tons and tons of juggling patterns. This is great. So we can find minimal juggling patterns in a really, really fun way. It all becomes about putting these rooks down. Okay, how can I do it? What are the different ways? And so we start to ask ourselves questions. And the first question we ask is, how many patterns are there? These minimal juggling patterns. So how many minimal juggling patterns of period n? So the nice thing is we've transformed the problem, right? Because now we say, oh, instead of trying to figure out all these different juggling patterns, we can say, look, it's like putting rooks down on this big board. We start thinking to ourselves, okay, well, what we'll do is we'll put the rooks down one at a time. So in the first row, we're like, okay, look, there's no problem. Pick any place you want. Great. I have n options, which means that when I put my first rook down, I have n possibilities. Okay, good. Well, what about my second rook? Well, all right, so we can put our second rook down. Now, when we put our second rook down, there's already one rook above. We can't put in that same column, so we've lost the one place to put it. Well, that means we don't have n options. We have n minus 1, one less. Okay, so now we put the second rook down, n minus 1. What about the next rook? Well, we go to that third row. Okay, we were looking for places to put, and we say, well, look, I can't use anything in the same column as the previous two. That knocks two choices out, leaving n minus 2 choices to go, and so forth and so on. So as we go down, these are what we see. And so the number of rook placements is this product. But it has a great name, right? We've seen this before. This is n factorial, or n. Yes, n. Exactly, n factorial. So this is fantastic. It's wonderful when we have an ability to answer a nice question using simple numbers that we've seen before. So finding minimal juggling patterns, great. No problem. We can do it. So let's do it. Let's do a really small case. So find all minimal juggling patterns for n equals 3. And we've set ourselves up here by putting down a nice little 3x3 board. Okay, so let's grab ourselves 3 tokens. Here's our 3 tokens. And we just have to be methodical and go through all the options. So here we go. There's our first one. 0, 0, 0. Good. Well, now what's next? Well, okay, we can swap those two. And what do we get? Well, we'll get 0, 1, 2, right? 0, 1, 2, right? So when you read off the patterns, remember you're just going down each row and saying which part got the token. Where's that rook at? That tells you the throws. All right, well now let's try another one. Okay, here we go. 1, 2, 0. Now you might say, wait a second. Isn't that essentially the same as 0, 1, 2? We'll get to that. We'll get to that. It's a good question. Good question. All right, but let's keep going. Another thing we could do is right there, and that's 1, 1, 1. Okay, great. Well, what else can we do? Well, here we go. There's another one. 2, 2, 2. And last one. 2, 0, 1. That's it. And we know that's it because how many do we have? We have 1, 2, 3, 4, 5, 6. We have 6, right? And how many should we have? Well, 3 factorial is 3 times 2 times 1 is 6. We should have 6. Ha ha! Success! We did it. Okay, good. Well, now what can we do? It seems pretty easy, right? So we can find all these minimal patterns, but what do we do once we have just the minimal ones? We go back to where we started. Remember our observation that says, hey, we can add and subtract multiples of n. And then we said, well, look, every pattern we can take down to a minimal pattern, which means that we can start with minimal patterns and raise them up. And by looking at all the ways we can do that, we get all the patterns, all of them. So that's sort of this comment here. All the juggling patterns can be found by starting with these minimal patterns and adding multiples of n's to the throws. Let's look at a nice special case here. This case, 1, 1, 1. That is a really simple pattern. So the pattern 1, 1, 1 really just says keep throwing ones. It's easy. Boom, 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 boom. This is a really quick pattern to learn. A lot of people learn it fairly quickly. In fact, it's one of those patterns which you can almost learn mindlessly, just sort of while you're out there looking around. Very simple, very simple. Okay, well now let's modify it. And what we want to do, well, the period is 3, so that means we add a multiple of 3. And we can add it anywhere. So of course, it doesn't matter right now. And so what would we have? Well, instead of 1, 1, 1, we could write this as, say, 4, 1, 1. And say, hey, what's the 4, 1, 1? Sometimes that's used for information, right? Now, if we started with a 1-ball pattern and we increased one throw by a multiple of n, well, that says we should have 2 balls. In fact, that's exactly what happens. And you can check that by saying, okay, well, what's the average? Now, what does 4, 1, 1 look like? Well, the idea is fairly simple. What's going to happen is you're going to do a 4, and while that's up in the air, you're going to do a 1, 1. So 4, 1, 1, right? So up, back, back, up, back, back. Now, that's just part of it, but it's also going to happen with the other hand. So up, back, back. And what you'll do is you'll alternate. And then what you should do is get into the pattern, right? You want this to not, some gust of gravity, right? 4, 1, 1, 4, 1, 1, 4, 1, 1. You just want it to be smooth, always going at the same beat. So that's 4, 1, 1. All right? That's hard to remember. Just practice, practice. You can do it a little slow at first, and then it's just a matter of getting the cadence right. Okay, so there's 4, 1, 1. Let's add another multiple of n. Okay, well, let's add it to the next throw. So we'll put it into the middle. 4, 4, 1. All right. Now, this is an important pattern. We've mentioned it before, but look at how easy it was for us to find it. We said, oh, well, we have these minimal patterns. They're the rook placements. Here's a really easy rook placement. We'll just bump up a couple throws. There it is, not hard to find. So mathematically, easy. But practically, very, very hard. Thousands of years it went hidden from jugglers because it's not the obvious thing to look for. Now, what happens with the pattern 4-4-1? Well, the beautiful thing about the pattern 4-4-1 is it even describes what's happening to the throws. So what happens is you can do a 4, and a 1. And then you're going to do it again, 4, 4, and a 1. So that's what 4-4-1 does with one ball. So up, up, across, up, across. And the only thing is, you're not going to do it with one ball. You're going to be doing it with 3 balls, and they're all doing the same thing simultaneously, just shifted from each other. All right, let's see if we can get this to work. 4-4-1, 4-4-1, 4-4-1, 4-4-1, 4-4-1. Now, if you're very patient and you followed one ball, you'll see it always did the up, across, up, across, up, across. And there you go. Now, do we have to stop there? Well, I have to stop because I don't know how to juggle with more balls than this. But from a theoretical perspective, no, we don't have to stop. Now, what are things we could do? Well, there's lots of things we could do. So, for example, we could talk about things like, say, 7-4-1 or 4-7-1 or all sorts of things. See, we're able to start exploring patterns. And now we don't have to sit and wonder, hey, is this a pattern or not? We know. And knowing is a lot of the battle, probably more than half. Let's jump back for a second. I just want to make a note here when we talk about our board. See, we set up our board and we said, oh, look, these are our minimal throws, right? And that's how we're going to work it. And then later on we said, oh, yeah, but then we can bump our throws up by n. So it turns out that there's another way to think about what's happening with the board. And that is we can go through and add a little bit to our board. Namely, we add this symbol. Now, if you remember what this means, this goes back to our modular arithmetic. And it's not the equal sign, this is the equivalent. And so we talk about numbers are equivalent modulo n if they're different by a multiple of n. So that just says, look, if I'm talking about forming these juggling patterns, I can talk about saying, hey, what do I want to look for? So now what we do is we have here our nice board, and we can place our tokens. And so placing our tokens, and of course there's lots of ways to do it. So you can see, of course, we have a big number here, 5 by 5. 5 factorial, right? 120, big number. Okay, so when we talk about here, previously we said, oh, this would be like 3, 0, 2, 4, 1. And that's a perfectly fine pattern. But more generally, since we have this notion that we can build up, we really can say, look, the first throw, I can pick any number congruent to 3. Modulo 5, right, the period. And here I can pick any number congruent to 0, anything congruent to 2, anything congruent to 4, anything congruent to 1. Congruent is another way of saying equivalent modulo. So, in other words, as long as they differ by a multiple of n. So, really what we've done when we talked about minimal juggling patterns is in some sense we can say, oh, it's like we're taking our space of juggling patterns and we're carving them up and grouping them based upon how do they fit into this diagram. How do they fit in? And the minimal juggling patterns are in some sense just sort of like a nice representative element. There's one more thing we need to talk about. It's a kind of a really cool and also important idea. And when I say cool, it's like, wow! You know, the first time you hear it, it's like, what? That's so cool! So what we want to do is we want to talk about how many balls are there in a minimal juggling pattern. Because it depends, right? Some minimal juggling patterns might have 1 ball, some might have 3, or, you know, if we have very large boards, you might have 7 and 9, you know, any number. So it's important to answer the question, well, how many balls are there? Now, why is that important? See, what we're going to be moving towards is say, aha, if we can start with our minimal juggling patterns, and then we can count how many ways there are to bump up to, say, some number of balls, Then we can figure out how many patterns there are with the right number of balls. But how far do you need to bump, right? Because if I have 1 ball, I might have to bump a lot more than if I have 6 or 7. So we need to answer the question, how many balls are in a pattern? And the answer is beautiful. This is gorgeous. I love this. So here we go. The number of balls in a minimal juggling pattern is the number of rooks below the diagonal. Now it's marked here, in other words, below the diagonal, the part that's in pink. So however many rooks there are below the diagonal, that's how many juggling patterns. That's how many balls you need for that pattern. All right, let's test it, right? And of course, we're going to prove it. But let's try to convince ourselves first. So we start by doing rook placement, go row by row, and we'll just pick some numbers here. Doesn't really matter which numbers we pick. Just be careful, right? Wherever you put, you want to make sure there's no 2 in the same column and there's no 2 in the same row. So you should do a quick check. No 2 in the same row. Okay, good, we're good. No 2 in the same column. Great, good, perfect. Okay, so now we haven't written down the pattern yet. We haven't even said what the pattern is. We'll do that in a second. But without saying anything, without writing anything, how many balls? Now, if we believe this statement to be true, we just say, okay, well, how many are in the pink? 1, 2, 3. 3 balls. Let's test it. All right, so first let's write down the pattern. So it's a 2, 4, 5, 0, 2, 5. Okay, 2, 4, 5, 0, 2, 5. All right, great. And that is a pattern. You can check it. But the point is you don't have to check it. It's guaranteed to be a pattern. Every single rook placement that we have on this board that we read off always is going to be a juggling pattern. Now, let's add up these numbers. 2 plus 4, 6, plus 5, 11, still 11, plus 7 more makes 18. So these numbers add up to 18. There's 6 throws, and so that would be 3 balls, 18 over 6. Aha! As the Klingons would say, kapla! Which, of course, is Klingon for success. All right, well, that's just one example. Okay, maybe I rigged it. All right, okay, all right. We'll start moving these around a little bit, and okay. Maybe, how about that one? Oh, no, that's 2 in the same row. Can't have that. How about there? Okay, all right. That looks good. I don't have 2 in the same row. I don't have 2 in the same column. All right, what's that pattern? Well, okay, we read it off again. And 3, 1, 5, 1, 2, 0, right? 3, 1, 5, 1, 2, 0. Okay, it's a juggling pattern. Now, how many balls do you need? Well, it better be 2, right? Because there's only 2 balls here that end up down in that pink part of the board. Okay, well, let's see. 3 plus 1, 4, plus 5, 9, 10, 12. Okay, 12. Divide by 6, because that's the period. That's 2 balls. Oh, nice! It's working! It's really working! All right, are you convinced? Should we do one more? How about, instead of just doing it, let's try to shoot for something. Suppose I want to have 4 balls down below. Okay, well, all right, that means I've got to really squeeze in. All right, 4 balls. Let's see, we can try, that would have 4 balls down below, right? Right, because we've got 4 balls in there. Of course, then we have to finish up. Let's see. What columns we haven't used the last 2 columns yet. We haven't used the first row, and it looks like we haven't used that row, right? So just check. No 2 in the same column. Good. No 2 in the same row. Good. Okay, so what's the pattern? Well, 4, and then here is a 5. So 4, 5. There's a 3. There's another 5. Here's a 3. And there's a 4. 4, 5, 3, 5, 3, 4. Okay, well, that's a pattern. We claim 4 balls, right? Okay, well, let's see. 4 plus 5, 9, plus 3, 12, 17, 20, 24. Numbers add up to 24. Divide by 6, and we end up with 4 balls. Aha! Beautiful! It works! It really, really works! Okay, now, why is it true? It turns out the proof is really good. It's a beautiful, beautiful proof. So the way we're going to do it is we're going to add up the throws, because that's how you figure out how many balls you need. You add up the throws. So remember, if you see a sigma, it's a Greek letter, and whenever we see it, we think of adding. Sigma for sum for adding. So add up the throws. And now we say, well, look, the throws correspond to the rooks, right? So for every rook, we get a throw. So we're going to add up the rooks. And now we add up the numbers that are in the cells. Now, there was a formula for that. So the throw, you found it by taking the column you were in, subtract the row that you're in, and then you're going to add n if you're in the pink. Remember, we had that correcting term. So we wanted to make sure our terms were not going to end up being negative. Okay, so there we go. There's our sum. Now, here's where rook placements are really, really handy. Because what's happening? Well, we're going to have a rook in every single column. So there's a rook in column 1, in column 2, in column 3. So as we add up over all the rooks, we're going to get column 1 plus column 2 plus column 3 all the way up to column n. Once and only once for each one of those numbers. Also, same idea. Look, there's a rook in every single row. So when we group the rows together, we're going to get 1 once, we're going to get the number 2 once, and so forth, all the way up to n once. So these are our rows grouped together. And now the last part. Well, what happens? Well, we're going to add an n every time we're in the pink. So we're going to get an n times the number of rooks that are in the pink part. And now we come to the thrilling observation that if I have 1 all the way up to plus n, and then I subtract 1 all the way up to plus n, I get 0. They cancel. Which means that we're left with n times the number of rooks in the pink. Now divide both sides by n. Because remember, the number of balls is the number of throws. And so we come to the conclusion that the number of rooks in the pink region, which is the number of rooks below the diagonal, is the number of balls that you need. Ah, that's so good. So good. So we're setting ourselves up. Now, we're going to actually be a little bit more refined and talk about how can we count, for a particular period n, for a particular number of balls b. What are these numbers? What do they look like? What are some properties that they have? But before we do that, we're going to do a little bit of a detour and have some fun. All right, so some good stuff to look forward to coming up soon.